3.2, Logarithmic Functions. So this is a paragraph from the textbook. I just really like it. Defines a logarithmic function, and it also shows you how logs and exponents are inverses based on the idea that they are reflected over the line y equals x. So when and that's not a straight line at all, but when we're working in math, we like to have inverses of things so that we can solve. If we're squaring, we have a square root. If we're multiplying, we can divide. If we're adding, we can subtract. Those are all inverse operations. So we need to have an inverse operation for exponents as well. So our exponential function is what we learned yesterday. F of x equals b to the x power. And then the inverse, and I'm not writing the b greater than 0, b not equal to 1. All of that is in this paragraph up above, right? I'm just highlighting the important part. So the inverse is the logarithmic or log function. So inverse, f inverse of x equals log base b of x. So those two are inverses. So this one, my log, or my x is my exponent, and in this one, my log is equal to my exponent. And we'll really work on making sure that you understand logs and you have the feel for logs today. So first is looking at the same equation, but in logarithmic form and exponential form. So if I have log base b of x equals y, then I can turn this into the exponential form, and the exponential form would be b to the y power equals x. So a lot of times when I'm changing them, I'll draw this kind of line here where I start at b and I go past y and around to my x. So when I change an equation from logarithmic form to exponential form, that's the process I'm using. These two are equivalent. So on this page, we're going to work on evaluating logarithms, and we're going to use specific steps for this. Our solving steps are going to be that we are setting equal to x. Then we are going to change to exponential form. Third, we're going to get the same base on both sides. And then our fourth step is going to make our exponents equal. So for this first one, log base 2 of 16, I'm going to set it equal to x. And then again, I'm going to change it to exponential form. So that means 2 to the x power equals 16. So my log base is now my base raised to a power. Logs are always equal to the exponent, right? When I take a log, I'm finding my exponent. And now I need to make that 16 into 2 to some power. So 2 to the x equals 2 to the raised to the fourth power. And so now my exponents are equal, and so x equals 4. For the next one, again, I'm going to set equal to x. So 5 raised to the x power equals 1/125th. 125 is 5 to the third, but it's in my denominator. So I can write it as 5 to the negative third power. So x is equal to -3. Next one, log base 3 of 1/27. So again, I'm looking for an exponent. It's like 3 to what power equals 1/27th. That's what logarithms are. So I set it equal to x. 3 raised to the x power equals 1/27th. 1/27th, let's see, 27 is 3 to the third, but it's in my denominator. So again, 3 to the x raised to the x power is going to be 3 raised to the negative third power, and so x equals -3. And our last one, we have log base 17 of 17. So we're going to make it equal x. 17 raised to the x power equals 17. And so we know we could just make this 17 raised to the first power, and so x is equal to 1. Basic properties of logs. So if I have log base b of 1, That means b raised to what power equals 1? Well, anything raised to the 0 power equals 1. If I have log base b of b, we just did this on the last one with log base 17 of 17, we know that b raised to the first power equals b. Let's look at this one, log base b of b to the x power. On this one, I have base b, and then I also have a base b for this b to the x power. And so I always tell students that this is like those inverses that cross each other out. We're just left with an x on this one. And you absolutely do not have to cross that out. It's not even really mathematically correct, but I've just found it helps my students remember. Just like if I had 2x divided by 2, sometimes we just cross those 2's out. So it's that same kind of idea. So again, not really mathematically correct necessarily, but it helps us. And then the last property is if I have b raised to the log base b of x. So again, here's our base b's again. That's just going to equal x as well. Same idea. If I have b raised to a power and I have log base b, those are inverses. So for the next two, we are going to evaluate. So the first example we evaluated by setting equal to x and solving. Now we're going to evaluate using log properties. So those are all the properties we learned on the previous page. So that means for this first one, I need to figure out 8 to what power is 512. So let's see, 8 times 8 is 64 times another 8 is 512. So this is going to be log base 8 of 8 to the third power raised to the third power. And so that is just going to equal 3. Again, I have a base 8 and a base 8, just a 3. And on this one, I have the same kind of thing going on. 22 raised to the log base 22 of 15.2 power, so just 15.2. So that's how we use log properties. Common log. A common log is base 10. And we make base 10 the common log because we work in base 10, we use it all the time. This is the one that is on your calculator. So if you see a log button on your calculator, it is base 10. And we don't write the 10. So just like with square roots, we don't put the 2 there. We only put numbers when we do cube root or fourth root or fifth root, any other root. But if it's a square root, we don't write the 2 because we just use them all the time. So it's understood. So this would be like when I just have the word log x, something like that, then I know it's base 10. The base 10 is understood. And sometimes we like to write in that 10 just to help our thinking. So you are allowed to do that. Just like when we started working with simplifying. And in order to simplify, we'd put the 1 there in front of the x, right? Same kind of idea. So if you need to add the base 10 to help your thinking, go right ahead. So now we're going to evaluate, and we're going to use those log properties again. So I know that this is base 10, and I know that 10 to the fourth power is 10,000. So log base 10 of 10 to the fourth. So I know that will just be 4, which makes sense. 10 to the fourth power equals 10,000. So remember, this is equal to 4 because 10 to the fourth power equals that, right? My log is my exponent. So I really want to make sure we understand that when we are taking a log, we are finding an exponent. This is 10 raised to the power of log 12, but remember, this is really base 10. So just 12 on this one. Log base 14, 14 is not, or sorry, log of 14. 14 is not a multiple of 10, so we're going to have to use a calculator. But I can still estimate my answer. So I know that 10 to the first power is 10. I know that 10 squared is 100. And so 14 is closer to 10. And remember, we're finding our exponent. So our exponent is somewhere between the numbers 1 and 2. So our answer is between 1 and 2 and closer to 10. Or sorry, closer to 1 because 14 is closer to 10. So when I do this on my calculator, I get approximately 1.15. Pay attention to directions on how many decimal places to use. On the last one, we have no real solution. If I take logs of negative numbers, it gives me a domain error when I use a calculator. But if we think about what logs are doing, we're finding an exponent that it would take to raise 10 to a power and get negative 11. And it is not possible to raise something to a power and get a negative number. I can only take a negative number, raise it to a power, and get a negative. And I guess even then it would have to be odd or something, right? So there's just no real solution here. Even when I take a number and raise it to negative exponents, all I am doing is making tiny, tiny fractions. I am not making negatives. So natural log is base e, because e is such an important number. We talked about that. It's the one that we always see for continuous growth. We see it with money. We see it in nature. And base e, the natural log, is written as ln instead of log base e. And there is an ln button on your calculator also. So instead of log base e of x, we write natural log of x. So just an ln. It's not an in. It's not the word in. N for natural, L for log. So now we're going to try evaluating these four. My natural log is base e, and here I have e to a power, so just 4.6. On the next one, when I go to take the natural log of a negative, it works like a regular log. There is no real solution. On the next one, this natural log is base e. So once again, I have inverses. I just end up with 4. And the last one I need to use a calculator on. You should definitely have a natural log button on your calculator, and you should get 1.95. So if we think about how E is about 2.718, then this sounds reasonable, right? So this is not quite 3. If I took 3 and raised it to the second power and squared it, I would get 9. And this is a little bit less than 3. This is a little bit less than squared. So my answer that I got makes sense. So this would be that exponent that I would raise e to. So what this means is e to the 1.95 power equals 7. That's what our same equation would be, but in exponential form. So when we take a log, we are finding an exponent. So now we're going to go ahead and look at sketching and analyzing a graph. So let's go ahead and rewrite this with a y. And then whenever I am graphing a logarithm, I always go through and change it to exponential form. So my exponential form would be 2 to the y power is x. And then when I make my table, I find it much easier to put my numbers in for y. It's so much easier to substitute for the exponent and then figure out what it equals. So 2 raised to the negative 2 power is 1/4. 2 raised to the negative first power is 1/2. 2 raised to 0 power is 1. Let's see, this is 2. 2 squared is 4. 2 to the third power is 8. So this should seem really familiar, but we're doing it backwards. And that's because we're really taking the inverse. So our x's and y's are switched from what we did before. So it should seem familiar. Before, this y row would have been our x's, the x's would have been our y's. So because logarithms and exponential functions are inverses, our x's and y's are switched. Our domain and range is going to be switched. Everything is going to be swapped from what we did earlier. So let's go ahead and graph it. Let's see, when y is negative 2, my x is 1/4. Negative 1 is 1/2. I find it's really difficult to graph this backwards one. Let's see, when y is 1, it's 0. Let's see, when x is 2, my y is 1, 4, 2, 8, 3. So we have a graph that looks like this. And it looks like I have an asymptote, just like I did when I was doing my exponential functions. But my exponential functions, I had an asymptote for my x-axis. Now it's on my y. So when I come up with my domain is from 0 to infinity and not including 0. So soft parenthesis on 0. My range, Now my y stretch all the way across up and down my y-axis, so negative infinity to infinity. Let's see, what's next? Our x-intercept is now 1, and our y-intercept is now none. So that's reversed from before. We have increasing on the entire function. So increasing on 0, infinity. We're continuous on the whole function. So continuous on 0 to infinity. And notice again, I'm not using that bracket on 0 because I'm not actually including it. So we're just making a parenthesis there. We have an asymptote, which is our y-axis, so x equals 0. And then our end behavior. So we can't say x goes to negative infinity on this one. So as x goes to 0 and as x goes to infinity, what is our f of x? What is our y doing? So as my x goes to 0, our y is going down the page, so negative infinity. As our x is going to the right, our y is going up. So as x goes to positive infinity, f of x goes to infinity. So here's just a quick comparison of logarithmic and exponential decay. Again, notice our domains. Oh, this is for both logarithmic growth and decay. Okay, I was thinking about exponential and logarithmic for some reason. So just where what we just did was growth where it's going up. And then if we have a value for b, so if our base is between 0 and 1, then we look at something where we're decreasing instead. Not terribly worried about that, but this I am worried about. So if we have an x plus 1 in parentheses, we know that these are always the opposite of what it says. So instead of moving 1 unit to the right, this is going to translate 1 unit left. We'll have some of these multiple choice on our test, on our Canvas test. This negative in front is going to reflect about the axis, x-axis, or in the x-axis. And the negative 2 is going to translate it down 2. And then our last one, the 5 being multiplied is going to give us a vertical stretch by 5. And x minus 3 in our parentheses means we are going to translate 3 units right. Well, this is it for our 3-2 notes. Have a good night.